All right, team, for today we're going to take a look at section 3.2, exponential functions. So just to give you a little introduction, an exponential function is going to look something like this. A times b to the x power. For a lot of our examples today, our a value is going to be equal to 1 just to get an idea of what this function looks like. But really there could be any kind of value out front of this b to the x term. There's two types of functions that you're going to look at with exponential functions. The first one is when your b value is going to be greater than 1. What's going to happen is you're going to get this kind of growth function. So you can see as your x values are going to be getting bigger, notice your y values are also getting bigger. So it's an increasing function, so we are going to have exponential growth. Now, if your x values are getting smaller as your y values are getting bigger, meaning you're going to have a b value somewhere between 0 and 1, this is going to give you a decay model. Okay, so you start out really, really big, and as your x values increase, your y's are getting smaller and smaller and smaller. You do have a third instance where if your a value is less than 0, meaning if your a value is if your a value is negative, you are going to end up with neither growth or decay. All right, let's take a look at a really basic exponential function. So we're going to graph f of x equals 2 to the x power. And the way that we're going to do this is we're just going to set up a table of values. So notice we have our exponent is actually our variable, so that's what we get to pick our values of x for. And I'm not going to get too crazy. I'm just going to pick some positive x values, I'm going to pick some negative x values, and I'm also going to pick 0. And I just want to see what happens with this function. Now, I want to make my life a little bit easier, so I might start down here with positive 3 as my x value. So this means I'm plugging in 2 to the third power, so this is 2 times 2 times 2, which is 8. And then let's plug in positive 2, so 2 squared. 2 to the first, of course, is going to be 2. 2 to the 0, a lot of folks are tempted to say 0, but anything to the 0 power is actually defined as 1. And then negative exponents. So remember that negative exponents are movers. 2 to the negative first power is equivalent to saying 1 over 2 to the positive first power. So 1 over 2 to the first power would clean up to give me 1/2. And the same idea is going to happen here with negative 2. So 2 to the negative second power would give me 1 over 2 squared, which would give me 1/4, and 2 to the negative third power would give me 1 over 2 to the third, which would be equivalent to 1/8. We do get a really nice pattern here that I just want to take a moment and point out. So if you start with 8, notice 8 gets cut in half to give you 4, 4 gets cut in half to give you 2, 2 cut in half is 1, 1 cut in half is a half cut in half is a fourth, and a fourth cut in half is an eighth. So we do get this really nice pattern that as we go in decreasing order in the table, you can see that your y values are getting cut by half. Or likewise, if you go with increasing x values, you can see that the y value is doubling. So that's what's happening with an exponential function, is you are increasing or decreasing by a constant multiple. So let's go ahead and plot these points. Plot them as best as you can. You're going to have to do a little bit of approximating. It's not going to be perfect on your grid. And then we can go ahead and play connect the dots. And so there is my first picture of an exponential function. Let's answer a few questions about it. So let's talk about domain and range. If we go back and we look at the picture, notice if I'm plugging in something for the exponent, I can pick anything for an exponent. I can have positive exponents, negative exponents, pretty exponents, ugly exponents. There will always be a y value that is going to be spit out. So my domain is from negative infinity to infinity. However, my range, notice my y values, like when I plugged in negative 3, I got 1/8. Well, think about what happens, say, for example, if I were to plug in negative 10, I would get 1 over 2 to the 10th, which is close to 0, but not exactly 0. If I plugged in negative 100, I would have 1 over 2 to the 100th power, which again is 1 divided by something that's really, really, really big, which is going to be close to 0, but not actually 0. And you can actually see that we are getting asymptotic behavior right here with respect to the x-axis. So for my range, my y values are getting really close to 0, but never actually reaching 0. So we would say our range would be 0 to infinity, not inclusive. It absolutely is a function. It's called the exponential function, but you can also see that for each input, there's exactly one output. So it's passing that vertical line test. For our asymptote, there is a horizontal asymptote, and I'll go back to the graph here and I'll just highlight it in yellow. We are getting really, really close to that line y equals 0, but it's never actually reaching 0. So there is a horizontal asymptote where y equals 0. Now let's look at the intercepts. It's never going to touch the x-axis. If y is never equal to 0, then you will never be touching the x-axis. So there is no x-intercept. There is, however, a y-intercept. And I'm just kind of making that a little bit bigger here on the graph. So I can see it right there in my picture. I can also see in my table, when x is 0, my y value is 1. So the only intercept here is the y-intercept. I don't see any symmetry with my graph, so we have no symmetry. And let's take a look at end behavior here. So as x approaches negative infinity, what is my y value doing? And as x approaches positive infinity, what is my y value doing? So let's go back to our picture and take a look. So as x approaches negative infinity means it's going this direction. It looks like my y values are approaching 0. They're getting really, really close to 0. And as x approaches positive infinity in this direction, well, my y values are just growing, growing, growing. So that means they are approaching positive infinity. So then I can complete my end behavior statement. And then my intervals here, it looks like the only thing I have is an interval of increase. As my x's are getting bigger, so are my y values. So we have intervals of increase, and that is happening over the entire domain of our function. And then this would be an example of an exponential growth, because again, notice as my x's are increasing, my y's are also increasing. And the other thing to take note of here is my b value is bigger than 1, so that tells me that I'm going to have a growth. I do want to go back to that initial definition here of our exponential function. Notice that there's nowhere on here where b is equal to 1. Okay, we have either b is greater than 1 or we have b is going to be between 0 and 1, but nowhere is there a definition for b equal to 1, because think about what that would look like. If your function was 1 to the x power, well, 1 to any power is always going to be 1, so that would actually just give you a constant function. So that's why we don't have anything defined for b equal to 1. All right, I want to talk about some transformations with this function. So let's look at this new function g of x, and let's define it as 2 to the x plus 3. So now there's a plus 3 right here going on with my x value. So that transformation means we're going to be moving this graph to the left 3 units. So what does that mean in terms of our table? So notice I've just kind of cut and paste my table over here. So if I'm moving the graph left 3 units, that means I need to take away 3 from each of the x values. That's how you move something to the left 3 units. So I'm going to go ahead, wherever I have an x value in my original table, I'm going to take away 3 from it. So 3 minus 3 is 0, 2 minus 3 is negative 1, 1 minus 3 is negative 2, and I'm just going to continue and do that. It was easier for me to start with positive 3. You're welcome to start with negative 3. And now these are my new points. So I'm going to graph the point negative 6, comma 1/8. And negative 5, 1/4, negative 4, 1/2, negative 3, 1, negative 2, 2, negative 1, 4, and 0, 8. So here's an example of my function shifted to the left 3 units. This is still a growth model, so that hasn't changed. And then this question down here is just note any changes from the original parent function here. Well, the only thing that's really changed, because my domain and range is still exactly the same, I still have a horizontal asymptote in the same spot. Looks like the only thing that's changed here is where my y-intercept is. So my y-intercept is now at the point 0, 8. All right, what happens if we take that 3 out of the exponent and we put it down kind of away from the x value right here? So this now gives us a vertical shift of up 3 units. So if you're going up 3 units, that means you are changing all of the y values. So in my original table of values here, I'm going to go ahead and translate my y's 3 units up. So from each of these y values that were my original, I'm going to go ahead and add 3. So 3 plus 1/8 is 3 1/8. 3 plus 1/4 is 3 1/4. 3 plus a half is 3 1/2. 1 plus 3 is 4. 2 plus 3 is 5. 4 plus 3 is 7. And 8 plus 3 is 11. And so now let's go ahead and plot these new points. Again, as best you can here. So there's about 3 1/8, 3 1/4, 3 1/2, 4.15, 2.7, and 3.11 is going to be a little bit off. And we can play connect the dots here. I still have an example of a growth function. And then my changes to my original parent function, well, my range has definitely changed. My y values now get really, really close to 3, and then they're bigger than 3, so 3 to infinity, not inclusive. That means my horizontal asymptote has also changed, and we can see that hopefully in the graph. Let me pick a different color here. We'll kind of just highlight that line. Okay, they get really, really close to 3, but don't actually touch it. My y-intercept has changed. My y-intercept, either looking at my graph, I can look at my table here. My new y-intercept is now at the point 0.4. And that also means my end behavior has changed. So end behavior here, as x approaches negative infinity, my y values are now approaching 3. And as x approaches positive infinity, my y values are now approaching positive infinity. So that bottom statement there for the end behavior didn't change. But because all of my values got shifted up 3, that did mean my end behavior for x approaching negative infinity did in fact change. All right, let's take a look at this function j of x. So this is defined as -2 to the x power, or the opposite of 2 raised to the x power. So this right here, this could be rewritten as -1 times 2 to the x power. So what happens here with that -1 means we are going to have a reflection over the x-axis. So is it growth or decay? Well, it's neither, because now you have an a value here that's less than 0. You have a negative a value, so it's not going to be growth or decay. It's still going to be an exponential function, but it's just going to be defined as neither. So if you are reflecting something over the x-axis, if our original picture would look something like this, a reflection over the x-axis is going to look something like that. So what's happening here is we have all of these same x values, but now your y values are changing. So we are going to be taking the opposite of all of these y values here. So I'm just going to put a negative sign in front. So I'm still working off that same original table, but I'm just going to have the negatives. And then hopefully you would believe me that this is what the graph would look like if you reflected it over the x-axis. As far as changes from our base function, there's a few. Our range has changed. We now go from negative infinity to 0 because we have that reflection. We're working with the opposite y values. Our y-intercept has also changed. We're now looking at a y-intercept at -1. Again, I can see that from my graph, or I can find that in my table there. We now have an interval of decrease. So notice as my x values are getting bigger, my y values are now getting smaller. And it is decreasing over the entire domain of the function. And the last thing that's changing here is my end behavior. So as x approaches negative infinity, what are my y values doing? Well, they are still approaching 0. Now they're approaching 0 from below. And as my x values approach positive infinity, so as my x's are getting really, really big, what are my y values doing? Well, my y values are going down to negative infinity. Let's take a look at k of x. So k of x is going to be defined as 2 raised to the negative x power. So whenever that negative sign is with the x value right here, that means we are going to have a reflection over the y-axis is what this is going to look like. Is it going to be a growth or decay? I'm not entirely sure yet. Why don't we look at our picture maybe to help us figure this out? Because it looks like I still have a positive bigger than 1 b value, but I'm not sure what that negative sign is going to be doing here. So if we're reflecting this over the y-axis, if this is my normal function, if it looks something like that, reflecting it over the y-axis is going to be doing something like this. So I'm going to have all of the same y values, but I'm going to be working with opposite x values. So I'm going to go through here and take the opposite of all of my x values, and I'm going to plot these points now. And connect the dots. So looking at my picture, I can now see that I'm going to be working with a decay function. So it wasn't enough just to be able to look at that 2, that negative there really did play a big part here. And what are the changes from the base function? Well, it looks like it's now just a decreasing function. So I have intervals of decrease over the domain of the function. All right, here's our last one. So this is L of x, and I'm going to define it as 1/2 raised to the x power. And this one looks a little bit tricky. So let's think about some manipulation here of this 1/2 to the x power. So remember how a negative exponent works. A negative exponent is also a mover. So 1/2 is equivalent to 2 to the negative first power. So if you wanted to, you could think about rewriting that. So we have 2 to the negative first power raised to the x power, and then my properties of exponents, whenever we have a power raised to a power, we multiply those. So this is equivalent to 2 to the negative x power, which is what we just did. So if we see just this function, L of x presented as is, I would see there's a b value that's going to be between 0 and 1. So I know that's going to be decay. And then I know that's going to be equivalent to 2 to the negative x power, which is what we just did over here. So it might even be nice to think about this one, okay, 2 to the negative x power. You could think about that as 2 to the negative 1 times x. 2 to the negative 1 you could rewrite as 1/2. So that's 1/2 raised to the x power. So then that makes that really clear that this is going to be a decay function without actually having to plot anything. So this is exactly the same as our last function. So this is exactly the same as k of x. All right, let's look at this inverse function. Again, same points that we've been working with since the very first problem, and let's plot its inverse. So I guess let me do the black one first. Let me go ahead and plot these points right here. So again, this would be just my 2 to the x. So there's that. And then in pink, I'm going to graph its inverse. Now, I have no idea what the actual inverse function is of this. So I'm just going to use what I know about inverses, where you swap the x's and y's. So all of my x's are now going to become my y values. And all of my y values for the original function are now going to become my x values. I don't know what the inverse is yet. We'll save that for our next lesson. But let's go ahead and plot these points and see what this function is going to look like. Oops. Sorry about that. I'm having a hard time graphing today, apparently. There we go. All right, let's play connect the dots. Oops, missed a couple. So there's my inverse function. Now, remember inverses are reflected over the line y equals x. So let me just kind of roughly sketch that line in. And I think that makes that look a lot more visually able to kind of determine that we have this inverse function is reflected over that line y equals x. So this pink line, whatever this function is going to be the inverse of the exponential function. Okay, so we end up with something that looks like this. So let's look at a little bit of the behavior of this inverse function. So let's look at all of the essential questions here. So domain and range. Let's start with domain and range. If I'm looking at my x values now, notice my x values are now getting really, really close to x equals 0, but not actually at x equals 0. So my domain is 0 to infinity, but not inclusive on 0. My range for my y values, well, notice this is going to go down to negative infinity for my y values. And at some point, this is going to go up to positive infinity and reach all of those positive y values. So my domain, 0 to infinity, and my range is now negative infinity to infinity, which makes sense. So our domain and range of this exponential function have flip-flopped with this inverse function. My domain of the exponential is now the range of the inverse, and the range of the exponential is now the domain of my inverse. This is still a function. Notice our exponential is a one-to-one function. Okay, it's passing that horizontal line test, and my new function, my pink one, the inverse, is still a function. So yes, it's a function. Now, what happened with my asymptote for this one? The asymptote here is now an x equals line. It's now x equals 0. My x values, if you notice, are going to get closer and closer and closer to 0, but never actually reach 0. Intercepts, well, let's look at the graph here. It looks like I have an x-intercept at the point 1, 0, or I could look at it at my table. And now there is no y-intercept. I'm never touching the y-axis. I'm getting unbelievably close to it, but I'm never actually touching it. And now for my intervals, well, I have intervals of increase now. And my intervals of increase are over the domain of this function. So I have a new domain here from 0 to infinity, and my intervals of increase are increasing over that entire domain. For my end behavior, as x approaches, in this case, we're going to look at x approaching 0, because that's what x doing. It's getting really, really close to 0, but never actually reaching 0. So what are my y values doing as x gets close to 0? Well, my y values are going down to negative infinity. And then as x approaches, let's see what x is doing on the right. Well, as x approaches positive infinity, it looks like my y values are doing the same thing. My y values are also increasing there. And then symmetry, well, this one has none. All right, let's just write a couple of new functions here that's going to move this f of x function to do some different things. So if it's going to go down 5 units, let's call this function g of x. That's going to be f of x. So 2 to the x and going down 5 would mean we'd have 2x minus 5. If we want to go left 4 units, we'll call this guy k of x. Well, if it's going to go left, it's going to be up there with the x. So this is going to be x plus 4. It's going to be opposite of what we are thinking. And then reflection over the x-axis means we're going to have that opposite out front. You are welcome to write this, if this just helps your brain to see this, as negative 1 times 2 to the x plus 4. And then this last one has a horizontal asymptote at y equals 10. Well, we'll call this function L. If it's going to have a horizontal asymptote at y equals 10, I'm just going to do a super rough sketch here. Let's put 10 right here. And it's going to have a horizontal asymptote. Maybe it's doing something like this. Well, we're going to have that original, say, 2 to the x, but now if it has a horizontal asymptote at y equals 10, that means it's been shifted 10 units up. So it would be plus 10 on the end. All right, let's talk just a little bit about the number e. The number e is very similar to like the number pi, where it is an irrational number. You can never write it as a ratio of two values. Approximately, e is 2.71828, 45, 90, 45. Those are all the digits I know just by heart of e. And e is referred to as the natural number. It's going to show up in a lot of application problems, especially for you folks who are doing some type of like science or biology program. You're going to see the number e a lot with certain growth models. It's also referred to as Euler's number. I know you want to pronounce that as Euler, but it's pronounced as Euler. And the other big thing I'm just going to say about the number e is it's the base of the natural logarithm. I know that means nothing to you right now, but it will after our next couple of lessons. This piece right here is just kind of like how e is getting defined and where this number comes from. So if you look at this right here, if this would be our function, 1 plus 1 over n, and that whole entire quantity raised to the nth power, as you pick e values that get really, really big, so here we just have a little table of values. I just stole this from the internet. So as as n gets really, really big, so let's start looking at like 100 and 1,000 and 100,000, all these values, you can see that it's going to start to approach this number e. So this is what's happening. This is how e is defined. It's getting really, really, really close to this 2.718281828 45, 90, 45. It's getting really unbelievably close like that. So here's this number e. You can see this here. It's this constant that's being graphed. And then here's this function. So it's just growing and it's approaching. It's getting really, really, really close. So it's asymptotic to this number e. If we wanted to actually graph e, we certainly could. And actually, it might seem kind of weird to graph it, but it's really not. So I'm going to pick my same kind of range of x values here. And then this is where you would definitely want a calculator to go ahead and plug them in. And you have an e button in your calculator. It's on the left-hand side, just to the left of your number 4. You're going to have to hit your second key to access it. And I'm just going to type in e to the negative 3. And I'm going to do e to the negative 2. E to the negative 1. I'm just kind of approximating. E to the 0 is going to be 1. E to the 1 is going to be that 2.71828. And then we'll have e squared. And then we'll have e to the 3rd, which is going to be way too big for my graph. So I just wrote down a few decimal points. So let's just kind of approximate this. Negative 3, your y value is unbelievably small. Negative 2, it's still really small. Negative 1, still really small. 0 is 1. 1 is just about 2.7 or so. 2 is just bigger than 7. And 3 I can't fit on my grid. So you can see that it doesn't look a whole lot different here. Okay, that would be my e to the x function graphically. Notice it is a growth because e, again, is about 2.7 or so, so that value is bigger than 1. So it is an example of a growth model. So you could certainly be graphing things with base e. Don't be scared of it. It's just a number.